Your honors project this semester is the study of elliptic curves. Now, elliptic curves are curves of the form y squared equals x cubed plus ax squared plus bx plus c, with some restrictions on a, b, and c. Now, in general, if you graph a curve of this form, the graph will take one of four possible shapes. One of the very typical shapes, something like this. Another common shape has kind of two pieces to it, something like this. And there are some other possibilities also. The curve could look something like this, or maybe like this. Now, one thing to notice about all four graphs is that the graphs are all symmetric across the x-axis. That's because if I replace a y with negative y, then the equation is unchanged. So all of these have symmetry from top to bottom. Now, elliptic curves are going to be at the top two types. So we want to exclude the ones that have graphs with self-intersections, like this first graph, or cusps, like the second graph. And the way that we can exclude those is by looking at the discriminant of this equation. Now, in your homework, you calculated a formula for the discriminant, and what you should have gotten is this. The discriminant is negative 4a cubed c plus a squared b squared plus 18abc minus 4b squared minus 27c cubed. If we insist that the discriminant be non-zero, then that eliminates the possibility of cusps or self-intersections. And you only get examples like the top two. So in all of our examples, we're going to be making the assumption that the discriminant is non-zero. And for any particular example, you can simply substitute the coefficients a, b, and c into this formula and check that we get a number which is non-zero. Now, when we talk about addition of points on elliptic curves, we could use either of these types of graphs. One of the things that they have in common is that in general, if you pick 2 points on the graph, P and Q, and you draw the line through P and Q, then that line will intersect the curve at a third point. Same thing here. If I pick P and Q and draw the line through P and Q, that line intersects at a third point. So I'm typically going to draw graphs of this first type, but exactly the same thing that works here is going to work on graphs of this second type. Now, when we define the addition of points on a curve, there are actually a few cases we'll have to consider. Here's the most common case, though. If P and Q are separate points on the curve, then when you draw the line through them, they intersect that curve at a third point. We're going to call that point P star Q. And then to get the sum of P and Q, we reflect that point across the x-axis. And this new point is called the sum of P and Q, P plus Q. Now, odd things can happen. For example, if P and Q are the same point, actually, before we deal with that, something that might happen is that if this is P and this is Q, then when we draw the line through P and Q, it might be tangent to the curve at Q. So when we have a point of tangency, we're going to consider that to be an intersection of multiplicity 2. So we'll say that P star Q is Q. So we're thinking about this purple line as intersecting the graph in 3 points, P, Q, and then Q again. Q counts twice. So P star Q is Q, and then we'll reflect across the x-axis to get P plus Q. Another strange thing that could happen is we might want to add a point to itself. We might want to take P plus P. So that means that I need to draw a line that intersects twice at this point. Well, in that case, if it intersects here twice, then it's a tangent line. So I'll draw the tangent line to the graph, find out where that crosses the curve. That will be P plus P. Or sorry, that'll be P star P. And then when I reflect across the x-axis, I get P plus P. So to repeat, if I want to add a point to itself, I'll draw the tangent line to the graph at that point, find out where that tangent line crosses the graph, and then reflect across the x-axis. Another special case to consider is what happens when P and Q lie on the same vertical line. Well, when the points lie on the same vertical line, there's no third point on the graph. It's going to intersect P and Q each with multiplicity 1, and we don't see a third point. So this is when we added an extra point to the graph at infinity. So we said that every elliptic curve is going to also contain one extra point at infinity. And we're either going to think about that being as infinitely far up or as infinitely far down. We'll consider those to be the same point. So a vertical line will cross the graph at 3 points, P, Q, and then this third point at infinity. Now, starting with graded homework 5, instead of calling that infinity, we're going to call that point O instead. And once we start adding points, we'll see why we like to call it O. In fact, we can see one example here. Suppose now I wanted to take a point P and add O. What is P plus O? Well, O is infinitely far up, so we'll draw the vertical line through O and P. So this would be P star O. And then we will reflect it across the x-axis. We get that P plus O is the same as P. So P plus O equals P. So that means that O is acting like an additive identity. And in fact, when we take the points and include O, the points on the curve and include O, then we do get a group where O acts as the additive identity. So back over looking at this example, if I have 2 points that lie above each other, P and Q, then when I add them, I get the point of infinity, which is O, so O would be P star Q, but when I reflect it, I still get O, so O is equal to P plus Q. So in other words, when I add P and Q, I get the additive identity, which must mean that Q is the additive inverse of P. So when I have 2 points that are above each other, they're additive inverses of one another. And then last of all, let's say that we have a point here on the x-axis, and I want to add it to itself. But here, when you add a point to itself, we'll get the tangent line, but the tangent line is vertical. So P star P is going to be O, and then when I reflect it, I get O again. So when P is a point on the graph where you have a vertical tangent line, then P plus P is equal to O. In other words, 2P is equal to O. So that means that points on the x-axis where you have a vertical tangent have order 2 in the group.